I'm Dr. Wasif Razak, and I'm going to chair this session with my colleague, Ms. Asha Afzal. And first keynote speaker for this session is Professor Valentina Casalino. And she is an associate professor in Department of Material Science and Technology at Politecnico di Torino. Her research activity have been mostly dedicated to design, fabrication, and characterization of joining materials and joints for advanced ceramic composites and ceramic metal components. She is also working on developing characterization and testing of material like custom glasses and glass ceramics and their composites for extreme application and energy production. Now I would like to request Professor Valentina to start her talk. Please, Professor, over to you now. And her topic of presentation is integration and joining of CMC. Over to you, Professor.
Okay, thank you very much for your kind introduction. Can you see my screen? And can you hear me?
Yes, we can hear you.
Okay, and you can also see my screen?
Yes, sure, we can see your screen also.
Okay, okay, so sorry, I think just a moment. Okay, so thank you for your invitation, and it's a pleasure for me to participate in this conference. And as you said before, I will give you an overview on integration and joining activity on CMCs at Politecnico di Torino in Italy. Just a brief introduction on my university, that is one of the biggest university in Italy. Politecnico di Torino is located in the north part of Italy, close to France. And as you can see from the slide, there are several schools of engineering, architectures, and some specific learning activity dedicated to automotive and design and other industrial subjects. At the moment, there are more or less 40,000 students that are attending our courses. And I want to underline also the presence of several centers that are born in collaboration within several departments in Politecnico di Torino, and we are part of this JTech Center that is in the red frame in this slide. It's a center dedicated to joining activities. So its name is related to advanced joining technologies, and is a sort of a hub for research on joining materials and joining processes. I'm part of the GLANCE team. GLANCE stands for Glasses, Ceramics and Composites, and we are mainly focused on research on this kind of materials. As you can see, several people are involved in this research group, and we are also working within different European projects as a coordinator or as a partner. And we also collaborated with different companies in Europe, but also in the US and outside Europe. This is the JTech Center. If you want to have a look to this center, you can go on YouTube, or you can search for information on the web page. As you can see from the pictures, there are several facilities and several equipments dedicated to investigation on materials in general and on joining processes. So several furnaces or other characterization devices to assess the behavior of the joints and of the joining materials. So we are mainly focused on research activity as on glasses and glass ceramics as joining materials. The idea is that we can design the glasses with a different range of composition in order to obtain specific thermal, mechanical, and chemical properties for the final application of the joint and the final application of the component where the joining material is located. So we are involved in this kind of research for several years, and we started our research more or less 20-25 years ago. And we developed this kind of joining materials for different applications for ceramics, but also for composites, polymeric based composites, or CMCs composites, or also for dissimilar joints, so CMCs to metals or to other kind of materials. Why we choose glasses and glass ceramics as joining materials? First of all, because they are versatile. We can define their composition, and we can tailor, based on different composition, the coefficient of thermal expansion or the wettability behavior on different substrates. In general, glasses are able to wet ceramics and to wet composites, ceramic-based composites, and then they can be used as joining materials in joining processes without applying any pressure. So this is very important for the technology transfer of these processes to companies. And then we can transform glasses in glass ceramics using controlled crystallization process, and this is beneficial in order to improve the creep resistance and the thermomechanical behavior of the joint. Then these joining material glasses can be also self-sealant at temperature above the softening point, and of course they are low-cost material and not affected by oxidation if compared, for instance, to metals or to metallic brazing alloys. Here you have an example of a specific glass ceramic that we studied in the past. It is based on alumina and calcium oxide, and we call it Ca. And it has been used to join the different kind of CMCs based on silicon carbide, but also different materials. It was used also for oxide composites, and we performed this the joining process at temperature close to 1500 degrees for a very short time, less than 10 minutes, in argon atmosphere, and without applying any pressure during the joining process. And at the end of the process, at the end of the joining treatment, the final joining material is a glass ceramic, and here you have the composition in the last cell of this table, the composition of the joining material that is quasi full crystalline material with this kind of crystalline phases. And this materials was studied and designed in particular for nuclear environment. And here you can see some nice pictures of joined silicon carbide based materials. And we tested also this glass ceramic under specific nuclear irradiation, and this glass ceramic was neutron resistant up to 530 degrees at 20 dPa. That is a sort of threshold for the behavior of materials in nuclear environment. And the most interesting result was that the thermomechanical properties of these materials of this joining material did not change after this test. So after morphological observation and after mechanical test, the structural properties of this glass ceramic material and also of the joined components were not changed. And we also tested some other composition of glasses and then glass ceramic for joining oxide-oxide composites. Here you have an example of the cross-section of a joined component, and here the base material to be joined are oxide-oxide CMCs. So they have a matrix of alumina and zirconia, and they are reinforced by alumina fibers. And also in this case, we applied glass ceramic. We used the glass ceramic as a joining material. And we tested it at room temperature and also at high temperature using a mechanical test, 4-point bending test at room temperature and at 850 degrees, according to the standard for this kind of mechanical test. And the behavior was very good, as you can see from the last column that indicates the mechanical strength of the joined components at high temperature. In this case, we also observed a slight increase in the mechanical strength of the joint, and this is probably due to a sort of sintering effect on the joined components. And we performed also other characterization in order to investigate the creep behavior, since the idea is to use these joined materials at high temperature. And here you have the results of some creep test carried out at 1000 degrees for 50 hours at a load of 40 megapascal in bending stress. And it was demonstrated that these joined components obtained by using this glass ceramic can be stable up to these conditions. We also studied other systems for joining CMCs, not only to other CMCs, but also to metals. This is an example of the same composites, so a matrix made of alumina and zirconia, and the reinforcement is given by this Nextel 610 that are alumina fibers, joined with titanium alloy, titanium 6 aluminum 4 vanadium alloy, and also in this case we used a glass ceramic as a sealant material. And here you have another activity carried out by Professor Smercetto and Professor Monica Ferraris that are involved in research on joining materials here at Politecnico di Torino. And also in this case, we used a different glass ceramic material to join metallic material, Inconel, to ceramic material for different applications. As you can see, there are some porosities in the joining material, but this is common for glasses and glass ceramics, and they are not detrimental for the thermomechanical resistance of the joint. Other activity regarded the study of a specific joining technique that we call the RM, wrap joining technique. RM stands for refractory metal material. So the idea is to use a sort of wrap of materials made of pure silicon and then a refractory metal. So in principle molybdenum, tantalum, or zirconium, or niobium, and use this wrap of materials to obtain the joint between different substrate materials. We tested this specific joining process on bulk ceramic and on different CMCs. Silicon carbide matrix reinforced by silicon carbide fibers, or silicon carbide matrix reinforced by carbon fibers. And the joining process was carried out at around 1400 degrees for 5 minutes. So here you have the result of this activity. we use this joining technique to join different kind of materials and different shape of materials. In this case, in picture A, you can see that we used also this joining material to join a silicon carbide based foam. And the final structure of the joining material that is shown in picture B is a composite material. So it is in principle an in situ formed composite material where the matrix is made of silicon and the particles, so the reinforcement of this in situ composite are molybdenum disilicides in this case, or in other, if we use different refractory metals, they are, for instance, niobium disilicides or other compounds. In the picture with the yellow frame, you can see also the result of oxidation test on this kind of joint, and we can observe that the microstructure was unchanged also after this oxidation test carried out at 1100 degrees for several hours, of course in air, to check the oxidation behavior of this joining material. Another activity regarded the joining of CMCs, oxide-oxide CMCs, using pre-ceramic polymers. This activity started just last year, and we obtained good results using a sort of silica precursor. It is a commercial silica precursor reinforced with nano silica particles, and here you have a macro image of the joined component. We also investigated the cross-section of these joined materials. As you can see, the joining seam is this in the center part of this picture. And also we tried to use other techniques to investigate the soundness of this joint. And here you have a micro CT analysis of the joining material. So we tried to see which is the structure and if there are some porosities at the interface of this oxide-oxide joined component. Another activity, I just give you a few information on another activity that we carried out for improving the mechanical resistance of the joint. The idea is try to do a sort of matching of the surface to improve the strength of the joint and to create the sort of interlocked surfaces. So we started from the macro scale, millimeter matching of the surface of the materials to be joined, moving to micro scale and nanometer scale. The idea is to use this modification of the surface in case of non-direct joining, so in case of joint obtained with some filler, and to increase the strength of the joint and the adhesion of the joining material. So we can use the preparation of the surface to remove the contaminants of the surface, or to obtain a sort of functionalization, chemical functionalization of the surface. But our activity focused on the texturing and to obtain a sort of increased roughness on the surface. So the idea is to promote the interlocking effect by the retention of the joining material in the joining area, and by improving the formation of anchoring points between the joining material and the surface. This is the idea of this mechanical interlocking, to create brush joints between the two surfaces in order to maximize the interface strength and to create a sort of a non-planar interface and non-planar contact area to increase the mechanical properties of the joint. And this is, for instance, one of the activity that we carried out. As you can see on the right, there is a silicon carbide composite that was surface structured, and in this way we increase the interlocking effect and the penetration of the brazing alloy. Okay, I will skip these 2 slides, sorry, because okay, I just want to show this activity concerning this modification of the surface in case of silicon carbide composite. The idea is to obtain a selective removal of the fibers using different condition of plasma etching that is based on different gases and different applied power and different exposure time. And the final effect is visible here on the left. This is the microstructure of untreated silicon carbide composite. And then you can see the results of a different etching treatment. And we did a sort of preferential etching of the fibers. And this was beneficial in terms of interpenetration of the brazing material inside this area of the fibers that have been removed by this etching. And we tried to check and to assess the real effect of this structuring by using a single lap offset test in compression. And untreated joined CMCs reached a strength of around 76 megapascal, while in case of these brush-like structured samples, the final result of the mechanical strength, the average mechanical strength was around 120 megapascal. So this is a very good result. We also tried, to do other activity by the modification of the surface using a sort of thermal etching of the surface. And this is the result in case of 6-SiC composites using different treatment at 1450 degrees for 2 hours and for 4 hours in a controlled atmosphere. And the best results have been obtained with this shorter treatment. It is possible to observe that there is a sort of matching on the surface, and this is beneficial for the retention of the joining material and for this interlocking effect. This is the result of these modified surfaces, this one on the bottom part of the slide. We tested the effectiveness of this surface modification process using a commercial brazing alloy, silver, copper, titanium alloy, and it was possible to observe that in case of modified surfaces, there is a good infiltration of the joining alloy if compared with the not treated samples. And this is the effect of this brush-like joint, where there is this modification for at least 10 microns starting from the surfaces. Okay, I will finish in 3 minutes, I think. I just want to show you the results of this chain-wave project. We worked also within this European project for the study of joining for silicon carbide and oxide materials. The idea is to try to replace the metallic tubes that are commonly used for this part of the components used in the steelmaking process, in the steelmaking industries, by using CMCs produced with a specific technique that is chemical vapor infiltration based on microwave. And we work on different kind of joints, butt joint and flat joint, accordingly to the direction of the fibers. And we focus our activity on selection of glass ceramics and brazing alloys for these two kinds of materials, so silicon carbide, and oxide CMCs. Just a few pictures concerning this activity on the use of brazing alloys for silicon carbide. We tested a specific joining material based on nickel, chromium, and iron, and we solved the most important infiltration of this brazing alloy within the open porosities of the composites by using modification of the surface, for instance, by introducing some additional interlayer, in this case, in the picture, molybdenum interlayer. Or the other activity regarded the use of a specific glass ceramic composition to join oxide CMCs. You can find more information concerning this test, this activity, on the Journal of the European Ceramic Society. And in this case, we tested these specific joints in some extreme environment by exposing directly the joining material and the joined components to this flame test in order to reproduce the steel making environment and the final conditions where these components were be placed. Okay, sorry, probably my talk was too long, but this is the end of my talk. So thank you for your kind attention, and I'm available for questions, if any. So thank you again for inviting me here.
Thank you so much, Professor Valentina, for this informative and descriptive talk. I would have a question from Ms. Aisha. Ms. Could you
Hello, Professor. Can you explain the selective removal of fibers from the composites?
The selective removal?
Yeah, selective removal of fibers from composites.
Okay, so just a moment, I will look for the right picture. Oh yeah, okay. So this is the selective removal. The idea is explained here. So the idea is try to do a removal of the fibers, or also of the fibers, but of the matrix, but in any case of one of the component of the composite, in order to create a surface that is not planar, but that is sort of matching due to the removal of the fibers. And yes, this is what we carried out. The idea is to put the samples of composites in a furnace, and using a treatment at high temperature for different time, try to have a sort of preferential etching of the fibers that are different in terms of crystalline phases, even if the chemical composition is the same, since the matrix is silicon carbide, but also the fibers are silicon carbide, but they have different crystalline structure. And so we can obtain a sort of corrosion of the fibers, starting from the surface, from the top of the surface. And then we were able to tailor the depth of removal of the fibers. And in my opinion, it is clear that for instance, 4 hours in the yellow frame, the removal of the fiber was complete. The treatment was too aggressive. So we try to reduce the time of the process and obtain just a few microns, let's say less than 10 microns of removal of fibers. And this was sufficient to increase the surface area and to increase the interpenetrating effect of the joining material. I don't know if it is more clear now.
Thank you so much, Professor. This is enough. Thank you.
Okay, I think we don't have any. Thank you, Professor, for this informative talk. Now we will move out to our next
okay, thank
speaker.
you to you.
Thank you. So our next speaker will be Dr. Muhammad Asif Javed from National Textile University. And his topic is development of chitosan and curcumin based aqueous polyurethane dispersion for textile finishes to improve the physiochemical characteristics of textile surfaces. So over to you, Dr. Muhammad Asif, please. You can share your screen.
Assalamu alaikum. Are you listening me? Hello.
Yes, we are listening you, Professor.
Okay. Hello. Assalamu alaikum. Bismillah ar-Rahman ar-Rahim. My name is Dr. Muhammad Asif Javed. I'm working as an assistant professor at Department of Applied Sciences, National Textile University. And Professor Dr. Muhammad Tahir Hussain is a mentor of our group. And today I'm going to present the development of chitosan and curcumin-based aqueous polyurethane dispersions for textile finishes to improve the physiochemical characteristics of textile surfaces. The graphical abstract of this research is this. First, we have prepared polyurethane dispersions, and then we applied on the fabric to make it antimicrobial, to show some antimicrobial potential. And after that, we also studied the tear resistance, rubbing fastness, and the color fastness of that fabrics. And the presentation layout of my presentation is consists of these contents. So, what is polyurethane? So polyurethane are the most versatile synthetic polymers containing urethane linkages that are formed by the reaction of isocyanate at the hydroxyl groups and that form a urethane linkage. And 100 of these repeating units make up make up the polymer backbone, which defines the most performance properties. So if we see that the polyurethanes family, so polyurethanes comprise of flexible polyurethanes, rigid polyurethane forms, coating adhesives, sealants, and elastomers, thermoplastic polyurethanes, binders, and the water dispersible polyurethanes. So what are the water dispersible polyurethanes? These are the binary colloidal system where stabilizing group containing Pu particles are dispersed in aqueous medium, in which the some ionic groups are present that helps to dissolve to disperse that material into the water. So here in this, there are some carboxylate groups on the polymer that help to disperse that material into the water. So intensive research has been carried out to develop and modify the chemistry of APUDs. The modification includes surface and the structural modification with novel materials. So it is imperative to develop aqueous polyurethane dispersions mainly due to the evolution of legislation toward the reducing the volatile organic concentration and the preparation of the environmental friendly products. So properties of water dispersible polyurethanes are they're easily dispersed in the water, they contain low volatile organic components, and they're non-toxic, odorless, and safe to use, and are environmental friendly. So they also show high initial bond strength, excellent heat resistance, and non-yellowing exposure to the UV light. That is the drawback of the conventional finishes of textile fabrics. In this research, we use chitosan, a biological material that is a linear polysaccharide composed of distributed beta-1 folding D-glucosamine deastellator unit and N-acetyl D-glucosamine that is estellator unit. It is made by treating shrimp and other crustacean cells with alkali sodium hydroxide. And another material that we use is the curcumin. The curcumin is the 1,7 base 4-hydroxy 3-methoxyphenyl and 1,6-heptadiene 3,5-dione is the active component present in the curcumin. So it is extracted from the roots of the Curcuma longa plant that is normally known as the turmeric. So owing to the component of curcumin has the ability to impart the several pharmacological effects, for example, antifungal, antibacterial, anti-inflammatory, antioxidant, and anticoagulant, anti-tumor properties. These are also used as a dyeing agents and these dyeing dyed fabric, for example, for some such as uses it as a dye on the silk fabric, and that showed a very good fastness properties. So applications of the water dispersible polyurethanes are used as coating, surface finishing, paper sizing, leather industries, footwear, flexible packing, automotive, contact adhesive, wood and furniture, textile industries. So they are extensively used in textile applications, especially so the spandex lacquer, textile laminates, breathable membrane clothing, PU coated garments, and buoyancy aids. So need of the project. In the textile industry, normally the formaldehyde-based finishes and binders are being commonly used as a coating material to improve the fastness property or some as a durable press finishes. Like the for urea formaldehyde press finishes are being used that contains the formaldehyde, which is the carcinogenic material. Based finishes causes allergic reactions and the skin diseases. So we have a best option to prepare the bio-based water dispersible polyurethanes to overcome these problems. Water dispersible polyurethane-based textile finishes are formaldehyde-free finishes. And incorporation of the biological molecules, for example, chitos and curcumin, into the backbone of PU has become of interest to many researchers. In this research, the synthesis and the characterization of the novel chitos and curcumin-based polyurethane dispersions has been prepared. So they are very safe, formaldehyde-free finish, pronounced resistance against the pathogenic microorganisms, improve the surface properties of fabrics. So in this research work, we use the IPDI, polyethylene glycol, dimethylol propionic acid, chitosan, and the curcumin. Actually, in this research work, we have used the blends of the chitosan and curcumin and increased in the every incoming sample. In this research work, first we prepared the pre-polymer by reacting the isocyanate with the hydroxyl groups that is formed by the reaction of NCO and the OH groups, which is further reacted with the dimethylol propionic acid. We use the hydroxyl groups of these materials to further extend this material, which is further. This is the dimethylol propionic acid, which is already incorporated into the pre-polymer, and in the next step we neutralize this material with the triethylamine. So this triethylamine as a base neutralize the acidic component of the DMPA. And after that, this is the pre-polymer. What does mean by the pre-polymer isocyanate terminated? This contains the NCO groups at the end of this chain, which can further react with the hydroxyl groups of chitosan or the hydroxyl groups of the curcumin, which is further extracted. And this bridge is actually the this part that have been written to reduce the structure of our presentation. We use three kinds of fabric for this. One of them is dyed with reactive dyes, and other is printed with pigment dyes, and third one is the white, having different blend ratios and GSM and PPI and EPI. PPI means peaks per inch, and EPI means ends per inch. And also we studied the stability of these materials that shows the stability up to the more than 4 months, and the high materials are not very much stable. However, the lower samples that contains a small amount of chitos and curcumins are stable as compared to the materials that contain more content of chitos and the curcumin. So we determine the solid content of the material by weighing the weight of the dispersing after drying and the weight of the diffusion before drying multiplied by 100. So these are some materials properties that we have assessed during our research. We have characterized our material using FDIR and electron microscopic analysis, thermogravimetric analysis to determine the thermal resistance of the material, and we determine the molecular weights of the materials using the gel permeation chromatography. And antimicrobial potential was done by using the discrete diffusion method, and the mechanical analysis was determined using the tensile stress. We have concluded our research work according to the FDI analysis. In the first step, we first reacted with the PEG with the DMPA, and further reacted with the IPDI. So in the pre-polymer, that is pre-PU, that showed that the isocyanate peak is reduced as compared to the pure IPDI, which is further neutralized with the triethylamine. And the neutralized group contains the peak of the neutralized groups is reduced as compared to the pure TEA material. And further reacted with the chitosan and the curcumin that shows the characteristic peaks of the both materials. And in the final polymers, no peak of monomers or the intermediate steps has been observed. After that, we studied our material using the GPC studies, and we determined the number average weight and the weight average molecular weight and the polydispersity, that is the ratio of the Mn and Mw using the GPC studies. And we found that the retention time of the material that have a high concentrations of chitosan and curcumin shows the highest molecular weight, and as it is also apparent from the chromatogram of GPC, because the retention time of this material has been reduced. So APUD5 showed the highest molecular weight because it have low retention time, and the molecular weight of polyurethane solutions were increased with increase in the concentration of chitosan and curcumin. And also it has been observed that the thermal resistance of the polyurethane has been increased by increasing the concentration of chitosan and the curcumin. This is the red line of this of aqueous polyurethane dispersion containing the highest concentration of chitosan and curcumin that shows the maximum thermal resistance as compared to the other materials. We have studied the coating of our finishes using the STEM analysis. As this fabric is showing that there is no concentration because it is untreated fabric, and this fabric treated with 2% emulsion finish is showing that there are small amount of uh, finishes appeared on the yarns of material. And here is the this material is treated with a 4% finish, and that shows highest concentration of APUDs over the fabric. So we also studied the biocompatibility of polyurethanes. We add these dispersions along with the blood of humans, and we found that these are biocompatible. And this is the material that contains the small amount of the chitosan and the curcumin that showed less biocompatibility, but with the increasing of the concentration of chitosan and curcumin, the biocompatibility of the material has been increased. So we also determine the antimicrobial potential of the material, and all the materials shows the antimicrobial potential against the positive bacteria and the negative bacteria. And we use E. coli, B. subtilis, and S. aureus for this research of for these studies. We also study the washing fastness of the dyed and printed fabric, and we have observed that there are less stains are appeared on the uh, on the multi-shaded fabric using the small amount of the concentration. When with increasing the concentration of the finish, the washing fastness has been decreased. We also determine the dyed color fastness rubbing using dyed and the printed fabric, and we found that with the same observation observed here, that the smaller concentration of materials showed good fastness property as compared to the material that has contains the highest concentration of curcumin and the chitosan. Similarly, the color fastness superspiration was observed, and that showed a similar result. But we found that here in there is not much big difference as compared to the lower concentration and with the higher concentration of the materials. And also we determine the tensile stress strain of the materials, and this is the graph of 2% of APUD. In this, and this here is the red line is showing that the treated fabric, and the bluish line is showing that the untreated fabric. So the warp, the tensile strength of warp alongside the warps is increased using the aqueous polyurethane dispersions, and the similarly alongside the weft, the same effect was observed. The aqueous polyurethane finish has increased the tensile behavior of our materials. And similarly, with the 4%, the same effect was observed as by using the aqueous polyurethane finish, the tensile strength of our material was increased along the both sides, along the warp and weft side. Conclusions. So in this research work, novel aqueous polyurethane dispersion based antimicrobial brittle finishes were synthesized by varying the molar quantities of chitosan and curcumin in PU backbone, and FDR confirmed the structure of our material, and it was observed that containing lesser amounts of the chitosan and curcumin showed excellent miscibility with the PU, which leads to the improved stability of the dispersion. The SEM images revealed that the untreated textile surface has no dispersion on the surface sample, and the sample treated with 4% of dispersion showed more concentration of PU on the surface of the fabric as compared to the 2% of the finish. And all the chitosan and curcumin-based water dispersible polyurethane emulsions revealed almost comparable antibacterial performances against the tested bacterial strains. And the fact of the APUD coatings on the color fastness properties such as perspiration, alkaline and acidic, and rubbing and washing of the coated of dyed and printed polycellulosic textile revealed that all the fastness properties were improved significantly after using the APUD. And thank you very much for your attention. So if you want to ask any questions, I'm here.
Yes, thank you so much, Dr. Mohammad Asif. It was a very informative talk. I have a few questions for you. Like first question is, you are talking that you are applying the chitosan and curcumin finishes like with polyurethane on the textile on the textile fabric or fibers. My question is like, chitosan have some charge, like it also have positive charge, but a small amount of negative charge. So when you obviously a textile is going to dye before final application. So does this charge will also affect the dyeing properties of the fiber? Because obviously these similar charges will repel each other, so it might affect the dyeing ability of the fabric or fiber on which you are applying this dispersion. So did you ever think about it? Yes, okay.
Yes, actually, we determine the fastness properties of the fabric to check that the dye is releasing from the fabric or not. Actually, this is applied at the end of the fabric, and we use a small amount of the concentration. And in this my research, I showed that the smaller concentrations are better as compared to the material that is using the highest concentration of chitosan and curcumin-based polyurethane dispersions. So as you are asking about the negative charge is not the issue here, because we use many of the anionic dispersions, special softeners, and because that are not very much of highly concentrations, although their affinity to the fabric is very low, but they are used for the hydrophilic finishes. So that is, I think that there's no such factor been observed on the fabric, and we use therefore on the reactive dyes, and the reactive dyes are stored by much better substantivity to the fabric. So I don't think so that this is the issue that the dye may release from the fabric.
Thank you so much. Dr. Asif, we have another question. Can you explain the emulsion stability? Is it after application or before application?
No, dispersion stability is the material, is the pure emulsion, how much time it takes to get to separate out. For example, it's a pure chemical. Before we did not apply on the fabric, it's a pure chemical. Sometimes the dispersions get separated, and their shelf life is very small. They do not remains dispersed for the long time, and we have to use some emulsifier to emulsify them for the longer time, because we have to store them for a longer time. And if it's not a good dispersion, so it may not be used for the longer time. For example, if we want to use it after 1 year, so if it's not stable, we cannot use it after 1 year.
Thank you so much again, Dr. Mohammad Asif Javed, for your nice talk. So we will move to our next presenter. He is Mr. Waqas Javed from University of Wa, and he is going to talk about a study of the double lap adhesive joints between metal and composites fatigue behavior. Over to you, Mr. Wakas. Mr. Wakas, are you there? Could you listen to us? Mr. Wakas, we could not able to listen you. Could you please switch on your mic? We are unable to listen you. Mr. Wakas, could you please switch on your mic? Because we are unable to listen you. Sorry, listener, for the inconvenience, Mr. Wakas is going to rejoin, so we will have to wait 1 or 2 minutes for his rejoining. Sorry for the delay. Okay, sorry, Mr. Wakas is taking a little time for rejoining, so we can move to the next presentation. Then later on, we can ask him to rejoin. So our next presenter will be Dr. Fiaz, and we will have a video presentation from him. I think Mr.
Zahurullah.
Okay, so we will have a next presentation, video presentation from Dr. Fiaz Hussain, University of Agriculture.
Zahurullah.
Sorry, so we will have our next presenter, Dr. Zahurullah. He is from Queen's University, Belfast, UK, and his topic of presentation will be maritime applications of fiber reinforced polymer composites. So over to you, Dr. Zahurullah. Please continue.
Can you hear me okay? And can you see my presentation?
Yes, we can hear you, and we are able to see your presentation also. Thank you.
Okay. Thank you very much for this wonderful opportunity. So today I will be presenting my work on maritime application of fiber reinforced polymer composites. So this work was in collaboration with Mohammed Burhan, Scott Millen, Tommaso Scalisi, Levan, Giuseppe, and Brian Falzon. So I'm from the Advanced Composite Research Group in the School of Mechanical and Aerospace Engineering at Queen's University, Belfast. So the project that we are working on is the decarbonization of maritime transportation, a return to commercial sailing. So the Belfast Maritime Consortium, which is led by Artemis Technologies, so they won this UKRI project. And the project aim was to develop a zero-emission hydrofoiling ferries and a maritime transport system of the future. So the hydrofoil is this wing-like structure, so which is inside the water, and the way this work is that these boats are 100% electric, and these generate this minimal wake. So as you can see here in this video, that it's a comparison of two boats. So one is based on this hydrofoiling technologies, so which is flying over the water, and one is the conventional boat, which is generating a lot of wake behind it. And the aim of the project is to develop these type of boats, which is fully composite materials. So at Queen's University, we were mainly working on 3 projects. So one was on the impact modeling and also experimental validation. So Dr. Scott Millen was a postdoc on this project. And then another project that we were working on is about the hybrid metallic composite laminates for bolted joint. So Dr. Tommaso and Burhan was the researcher on this project. And then we also work on the application of AI in the failure protection of composite materials. So then Dr. Levan was the postdoc on this project. So due to the limited time, I will just give you some overview of the first 2 projects. So the first one is about the impact modeling. So as we can imagine that these boats can have 2 types of impact. So one is under the water, which is mainly the hydrofoil, which is this wing-like structure under the water. So it can either impact with some debris or can strike a large marine life. So in this case, we do 2 types of models. So one is the mesoscale model of the leading edge. So this is like the leading edge of the wing. So in this case, we model this this small section of the leading edge. And in another one, which is what we call is a global local model of the entire foil. So in this case, which is shown here, I will explain this in a minute. And another thing is that the boat can have impact above the water. So in this case, the hull of the boat can impact with the other vessels or maybe collide during the docking. So in this case, again, we do 2 types of models. So one is a mesoscale model, which is a small section, 100 by 150. And one is the global local model. So again, which is given here of the whole boat. So in the first model, which is this mesoscale model, so this is a composite structure basically, and we have this carbon protection here, and then there is a foam core, and then this is the rigid support behind it. And in this case, we are using a rigid impactor of 2 kilogram, and the velocity is 5 meters per second. So the impact energy here is 25 joules. And here we are using FEA modeling. So we are using about 68,000 elements. In addition to this, we have also considered ice impact, which can happen in this particular case. So it's a small block of ice of mass 0.05 kilogram. And in case of this ice, we are using this SPH to model it. And in this global local model, we then model a very small section with a full detail, but then we model the remaining part as a shell elements, which is computationally very efficient. And in this case, we're using about 106,000 elements, and out of this 38,000 are shell elements. In case of the hull, so we again using the mesoscale model, as you can see here. And again, here we are using 2 kilogram rigid impactor, 5 meter per second velocity. And again, we are using 10 elements through the thickness of the core. And for the global local model, again, we are model this very small section where we can have impact with the full detail, and then we model the remaining part as shell elements. And these are our damage model that we are using. So we are using both interlaminar damage model. So here we are using cohesive contacts. And then we are also using the intralaminar damage model. So we include both fiber-dominated damage, and we also include matrix-dominated damage, and we also include some nonlinear shear response of the matrix. So these are some results of the leading edge foil. So this is comparison of the mesoscale model and also the global local model. This is mainly for the delaminations, which are mostly the same. And similarly, this is the result for the global local model. And in this case, this is the matrix damage prediction from the local for the mesoscale model, and this is for the global local model. And again, this is comparison of the force versus time response when we do the impact with the rigid impactor, and this is for the ice impactor. And this is again the shows the kinetic energy and how it dissipate after impact. So here you can see that this was initially 25, and then after rebound, this is what the energy left, and the remaining energy which were dissipated in creating these damages. And this is for the ice block. And this is the result for the hull impact here. So again, we can see the delamination, the matrix damage, and we can also see some permanent indentation. And this is the force time response of this impact. And again, in this case, we are also perform some compression after impact tests. So we can see that this is the undamaged specimen, and then this is the damaged one. Here we also then perform some tests both on the plate panels and also on the on this leading edge specimens. So in this case, these are the different samples. So we are using about 6 samples for the flat panels, and then we are using 5 for the leading edge. And these are the different energies that we are getting here. And we are using both hemispherical tub, and we are also using flat tubs here. And this is just to compare the response of the experimental and simulation for the flat panels. So at 25.5 joule energy. And this is for the leading edge specimen using this hemispherical tub. And then this is the leading edge with the flat tub. So the red one again is the simulation, and the black one is the experiment. The second project that I would like to briefly describe is about this hybrid metallic composite laminates for bolted joints. As we know that the mechanical joints have a lot of positive points because these are reversible. We can do easy inspection and maintenance. But the problem is that we can have this stress concentration. So in our case, we are using this idea of the local hybridization within the bolted joint region, as you can see in this figure. So we are basically using this local hybridization to increase the bearing and shearing capabilities of these joints. And as you can see in this case, that this local hybridization, we have then 3 regions. So one is the hybrid region, one is the transition region.
Your slide is not moving anymore. It is on the 8th. It's the 8th slide. So could you?
Okay, just a minute.
Thank you.
Can you see it okay now? Can you see slide 9?
Not yet. Could you tell me the slide number in which you are talking?
It's slide 9.
No, but still, now yes, it's moved to 9.
Okay, sorry about it. Yeah, so as you can see here that we have these 3 regions here. So one is the FRP, and then this is the transition region, and then we have the hybrid region here in these hybrid metallic composite laminates. So our main idea of this project was to find out the interface fracture toughness between the metal and the composite. So in this case, we are using this modified transverse crack tension experiment to measure the mode 2 fracture toughness. So this is the equation for the mode 2 energy release rate. So mode 2 means that it's these are the different mode of the crack propagation. So we have the mode 1, and this is the mode 2, and this is the mode 3. So in mode 1, which is the opening mode, and mode 2 is the shear mode, and mode 2 is the tearing one. So here we are interested mainly in the mode 2. So and you can see that this is how the specimen look like. So in this case, we have one crack here in the composite, and we have this metal here and metal here. And then there are 2 cracks at the interface between the metal and composites. So in our case, as you can see that this is the equation for the G2. And in this equation, again, we have this X, so which is what we call is the correction factor for geometry and material elasticity. And this X is again a parameter of all these different parameters. So in these 2 equations, as you can see that we have some material parameters which depend on the elastic constants. And then we have some geometry parameters of this specimen. So in this case, for example, we have this alpha, which is the ratio of the length of this crack divided by the thickness of the laminate. And then we have the ratio of the H and H. So H is the total, and this small other H is for the metal part. And then at the end, we will calculate this mode mixity. So mode mixity is this is G2 divided by G2 plus G1. So this G2 is the energy release rate and in mode 2, and this is mode 1. So this means that if this parameter is 0, then it is pure mode 1. If it is 1, then it's pure mode 2. And if it is somewhere in the middle, so then we have a contribution of both modes. And in this particular case, we perform some parametric analysis to make sure that what should be the dimensions of these cracks in our sample. So for this case, we are doing a lot of simulations here. So we run about 20,000 simulations with all these input parameters. So we do some here parametric study. And then we create this type of FEA model. So as you can see that this is just a quarter of the sample which we can generate because of the symmetry. And here we are using the virtual crack closure technique, which is VCCT. And then the end result will be this X here, which is the correction factor, and this psi, which is what we call is the mode mixity. So the results, as you can see here, for different parameters, these material parameters. And here, as you can see that we are plotting this mode mixity with this alpha. So alpha is the length of this crack here, as you can see in this figure. So as you can see that for different material, if the alpha is very, very small, so this means that the crack length, this longitudinal crack length is very small. So this means that this parameter is less than 1. So this means that we cannot neglect the contribution of mode 1. Our main aim is to have a crack only in mode 2. So this means that if we keep this alpha greater than 0.5, which is you can see in this case, so then the then this mode mixity is 1, which is what we want in our case. In addition to this, we can also calculate this X here. So X is, as you can see, if you plot for different materials, if you plot this X versus alpha, and you can clearly see that if X is non-linearly dependent on alpha up to a value of almost 3 here. And then if alpha is greater than or equal to 3, the value of X stabilized, so leading to independence of alpha. Now, obviously, we want to satisfy both condition of mode mixity and this X. So that therefore we are choosing a value of alpha, which is 3 in this case. And based on this, then we can also then find out how we will calculate this X. So in this case, for example, we can run different simulations, and we can for different value of lambda and this rho, which are material parameters. We can run different simulation, and we can create this surface here. And then from this surface, we can use some surface fitting, and we can calculate this X from given rho and lambda. And this P is basically this matrix here, which is just like a polynomial coefficients. So based on this, then we prepare our experimental sample here. So in our case here, we have created this this sample, as you can see here. So we have composite in the middle, and then we have two steel on both sides. So for the composites, we are using this M79 UD600 prepregs. And then for the steel, we are using the cotton steel here. And to bond the steel with the composite, we are using this hex bond 679 resin. And these are the different dimensions of the samples here. So the sample size is around 250 by 15. And just to show some the experimental result here. So this is how the load displacement look like in this particular case. So because in this case, we have this transverse crack in the middle. So first, when you apply tensile load, what is happening is that first this transverse crack, which is just a matrix material there, so it will break, and then there will be some hardening, then there will be some plasticity of the metal part, and then some hardening again of the metal part. And at this point, which is the most important point here, at this point, the crack will start to propagate. And this point will be our this maximum load, that is what we will record here. And then from here, we calculate the stress. And then we will use our equation which is this equation here. So if we replace this sigma by this value here, and because we know X, we know all the material and geometry parameter, we will be able to calculate G2, which will be our fracture toughness, which is 1.08 in this particular case. And we also then verify with the DIC that the crack was propagating only in mode 2. And these are some post-mortem fracture analysis. So the proposed test setup allowed the hybrid interface fracture to propagate only in mode 2. So thank you very much for listening. And this is my email address. So in case if you want to contact, and if there is any questions, so I will be more than happy to answer.
Thank you so much, Professor. Your presentation was very good and very elaborative. We have no questions. Thank you so much.
Yeah, thank you.
Okay. Now we move to the next presentation. It is Dr. Hugh Kong, graduated in mechanical engineering from Donghua University, Shanghai, China in 1984 and obtained his PhD from the University of Manchester in 1989. He then spent 3 years managing the Coates Viala Marks and Spencer Fabric Center before taking up the lectureship in the Department of Textiles, UMIST in 1992. He served as Director of Postgraduate Studies in the school and chaired the postgraduate degree panels in the Faculty of EPS. His main research interests are in the fibrous structures such as yarns, non-wovens, non-fibers, and textile composites, and in the performance measurement, modeling, and recycling of flexible materials. Now he will present a composite of recycled carbon fibers. Over to you, sir.
So you can hear me?
Yes, please proceed.
Okay. Okay, I think got it. That took a while to find the share facility. Hey, good afternoon. My name is Hugh Gong. As you can see here, this is my email address. If you, in the end, if you want to discuss anything following the presentation, you are welcome to contact me directly. Hello, can you hear me?
Yes, we can hear you. Please carry on.
All right, sorry. Okay. So I'm based in the University of Manchester. As the chair first read out, I originally started mechanical engineering in China, in Donghua University, and then came to UMIST, which is now part of the University of Manchester. Did a PhD in nonwovens, really, but actually based on computer image processing, looking at nonwoven structures. So my talk today is on recycled carbon fiber composites. It's just to share with you some of the work we've been doing recently on sort of recycling of carbon fibers and also the composites made from recycled carbon fibers. I think most of you probably are very aware of these, so just very briefly, in terms of the background, we know, of course, carbon fibers are very high performing. It's been used in a lot of applications, especially in aircraft and other transport vehicles. And of course, they're also used widely in sportswear. The increase is forecast to be about 10% annually. And obviously, out of that, there will be greater waste generated as well, both in terms of production, because during production, there will be offcuts and things like that, waste materials. And of course, all materials have a finite span of life. At the end of these life, especially like aircraft, and all the carbon composites will be wasted. So there will be increasing amounts of waste. And coupled with that, I think we all know carbon fibers are very expensive to produce, mainly due to the energy-intensive process of making it. So there's a greater and greater sort of incentive to try to recycle carbon fibers, both in terms of course, the benefit economically, and also trying to preserve the environment, as carbon fibers are not biodegradable, so they will not, disappear from the environment as things, of course, accumulate, and this will become more and more of a problem. Now, in terms of recycling carbon fibers, currently there are 3 basic methods. Again, I think many of you probably are very much aware, so I'm just really briefly outlining these. So one of the most common ones is thermal recycling. Essentially, this is by burning the resin off, and then what's remaining is the carbon fibers. Okay, so the details, I think I'm sure you can find from literature. There are different ways of doing this. I think the fluid bed probably is the most common. And then the mechanical processing, essentially just crushing the waste material. And obviously the quality of the fibers out of this tend to be very poor, but it's very economical and easier to implement in terms of the actual recycling process itself. A third one is the chemical process. Essentially, this is by dissolving the resin, and then you leave the fibers behind. But of course, you have to be also very careful in terms of the chemical contaminants in the end. You know, what are you going to do after dissolving? You know, the chemicals you use, and also the resin. So there are, again, a lot of subtle differences between different methods people are developing and using. Now, in terms of the products, these are just some examples. This is some of the products made by a company that we collaborated with using recycled carbon fibers for cars. So these are mainly for non-structural applications, for panels in the car, and they estimated for this particular car, there were more than 30 kilograms of RCF non-woven material in there. But of course, if you look at the overall construction of the car, 30 kilograms is still quite a small part. But if these are all original sort of virgin fibers, then the cost will be much higher. And you also notice the material tend to be non-woven based, which I will cover shortly. Now, the main issue with recycled carbon fibers is that they tend to come in a very short, sort of a bit like a stable yarn production, which sort of they are stable fibers in the end, short. The other thing is that the length tend to vary dramatically. Some very long, some really very short. The other one, of course, because of the way the fibers are reclaimed, they tend to be very randomly orientated. And that's going to cause problems in terms of application, especially if you want to make them into unidirectional composites or making them into fabrics where you can control the fiber alignment, which actually is one of the most important aspects of what we have been trying to do. We had a large project in collaboration with several European partners and also Airbus, and also with several Chinese research organizations, and also the manufacturer of the, I think, well, it's quite famous in China. I think the latest commercial passenger aircraft manufacturer. The idea is trying to see if we can use recycled carbon fibers in aircraft and other sort of transport vehicles. Again, as I mentioned before, the problem with recycled carbon fibers is that they tend to be short and random. And that means in terms of the mechanical performance in the eventual composite, they tend to be a bit of a problem. So we were trying to develop composites for secondary components in the aircraft. Things like seats, for example, and door panels. We had a fairly long review article regarding this, which was published in 2018 in the Aeronautical Journal. And this is the information. I think if you are interested, you can find all the details in there in terms of looking at the background and the methodology and also the outcome of recycled carbon fibers.
Please turn on your mic. Dr. Yu, please turn on your mic.
Why? Sorry, you can hear now. Why?
Yes, we can hear you now.
Okay. Yeah. As I mentioned earlier, most of the recycled carbon fibers tend to be used in nonwovens because nonwovens are very flexible. We can use all sorts of fibers in terms of length and composition. We can mix it. It's not very fuzzy in terms of what the fiber property should be. So it is nonwovens are used very widely to produce products from all sorts of different types of recycled carbon fibers, including recycled fibers from clothing. And the processes of nonwovens tend to be much cheaper compared with traditional textile processes, things like weaving, because if you are going to do weaving, obviously you need yarns or filaments, where of course recycled carbon fibers are short and random. And the other thing with nonwovens is if you do the process properly, you can control the fiber orientation in a random way, so you can achieve an isotropic. Mainly, it's two-dimensional. It's difficult to do in 3D isotropic structures, but 2D, yes. And the product is also moldable, so you can make them into a 3D shape. And the surface texture tend to be smooth as well, so you can have fairly sort of good finishing on the surface. But primarily, it's just because of the flexibility of the process. So nonwovens are fairly easy to implement and very flexible in terms of what fibers we can use.
Please turn on your mic.
Oh. Oh, why? Anyway, I don't understand. That's why it keeps turning it off by itself. Anyway, when we use carbon fibers in the nonwoven process, there are certain issues we need to be very careful, because nonwoven processes involve a lot of mechanical opening of the fibers, and these are in this picture. You can see some of these things. I think if you are familiar with yarn production in textiles or nonwovens, and these are fairly obvious because we need to use lots of sharp wires to open the fibers up. And these mechanical processes can damage the fiber, the carbon fiber. And then more seriously, it can generate a lot of dust material. And carbon dust material is harmful to both machines because they are conductive. They can cause circuit shorts and cause lots of problems. And obviously, they are also harmful to human health. This is something that we have been struggling with. I will probably mention again later on about this particular aspect. So the process needs to be fairly carefully controlled, and a lot of the machines need to be optimized in order to process carbon fibers successfully. Why? So this is one of our partner organizations in Germany, DLR, the German Aerospace and Research Institute. They also tried using nonwovens by mixing fibers, sort of carbon fibers with other natural fibers. Because, as I said, carbon fibers are difficult to process, so we can mix it with maybe flex fibers to help make it more processable. So this is what they were trying to do. Now, as I said, carbon fibers are difficult to open mechanically because the fibers are brittle, they are easily damaged, and generate lots of dust. So as you can see here, they were trying to mix it in a closed chamber manually. But obviously, we are doing research, so this is just doing trials, essentially. And then using small non-woven rig, as shown here, is really very, very tiny. And then you are successful in making sort of graded non-wovens, graded in the sense that the mixing of the flex fiber and the carbon fiber can be different in the thickness direction of the non-woven. In other words, you can have a fully carbon fiber side, and then the other side is fully flex fiber. So this allows you to tailor the performance of the eventual composite depending on the application requirement. But obviously, this is done manually, so we needed something more mechanical. In our university, we try to use wet processing, wet non-wovens, essentially wet laying, which is a very common non-woven making process. For example, we use that to make wet wipes. A lot of these baby diapers are made using the wet process as well, filter materials. Essentially, it's based on the paper making facility. We had two different types of machines. One is the hand sheet former, essentially it's a hand machine by mixing the carbon fiber in fluid, and then you drawing it onto a filter essentially to form the hand sheet. The other one is using a mechanical device. I say mechanical, it's just basically electrical driven, so it's not hand sort of a held machine, but basic principle is the same. So you mix the fiber, you drain the water, and you form a non-woven. That's all. It's a bit like a paper making anyway. This is one of the things we tried. So we mix the carbon fiber with flex fibers, because obviously carbon fibers are rigid, hard to disperse, while flex fibers are hydrophilic. It's easier to mix in water. So we tried, in this particular case, 5 different samples with different mixing ratios. And then you look at the composites made out of that, and you find actually, if I just go back to remind you what number 2 is, because that seemed to be the best performing, which you can see here, which with 25% of flex fiber, we can get actually better performance compared with 100% carbon fiber. It's just because the way the fibers disperse in the composite. Now, if it's 100% flex, obviously flex fiber is not as good in carbon fiber as carbon fibers. And you can see also there seems to be a lot of void within the composite itself, which obviously for composite materials, voids are especially particularly negative for the performance. While the right-hand side is a 25% mixing, 25% of flex, 75% of carbon fibers. So you can see the void content is much reduced. There are not really any visible content voids. But as the carbon fiber content increases, the problem of fiber entanglement and the cluster becomes more serious. And that's when the composite material start the performance start to decrease. Anyway, the details of this work is published. So again, that's in the Journal of Aerospace. And again, we have a DOI link, and you can find the details in there. Now, in the latest work we've tried to do is we tried to see whether we can produce yarns from recycled carbon fibers. Now, if we can do that, the advantage is quite significant, because we can then use the yarn to construct fabrics, or we can use the yarn to produce unidirectional composites as well. And that really brings the recycled carbon fiber in line with virgin filaments in terms of how we can use it. Although in terms of performance, absolute strength will still be less. As we know, stable fiber yarns will not have the same strength as filament yarns. So that's the same way. However, if you produce twisted yarns, the characteristic of the yarn and the resulting composite will differ from filaments, because the yarns will have better stretch, and by using different levels of twist, you can also control the amount of stretch. So that way, we might be able to make composites which have better sort of toughness and also less brittle. And the degree of that can be controlled by the amount of twist, as I just mentioned. So there are a lot of potential benefits by doing this, and some of these benefits are quite significant. Based on that, we applied for some funding from the government. We had just about £750,000 to investigate this, and this is called the GRACE project. This is the full title. So it's called Green Recycling and Remanufacturing of Carbon Fiber Composites. And there were 4 of us involved in this. So these are the names. Costas Salty has just retired, actually. But he was one of the leading investigators of this project, although I took over once he retired. Anyway, this is also in collaboration with some organizations in China, including Shenzhen University. Now, the reason for that
Dr. Hu, please turn on your mic. Your mic is off.
Yeah, this mic, I don't understand it. Why it keeps turning off for no reason. Don't understand it. Anyway, so as I said, because we had a collaboration with Shenzhen University, because they developed a new process of recycling carbon composites. And one of our staff members was part of that project. It's essentially a chemical process, but assisted by electrical current. So what they found is they can use this to recycle carbon fibers from composites at room temperature. And there are no harmful chemicals generated, and also they can preserve the carbon fiber performance after recycling. In other words, the recycled carbon fibers, if you test the individual fiber, its performance is comparable to virgin fibers. But obviously, the problem is still what you're getting in the end are short fibers, because you can't have a very large vessel to recycle, very big pieces of composites. Even if you did that, the fibers that come out of that will still not be continuous, as what happened in the virgin state. I realize what's happening. Every time I click the slide, the microphone just mutes. Very odd. So I have to watch that every time I click something. Okay, anyway. So the idea we have for this one is trying to convert these short, random carbon fibers into a spun yarn. That is essentially the basic idea. But of course, to do that is not as straightforward as it may appear, because this is a simple sort of diagram showing what we normally do with yarn production, to spin continuous yarns from short fibers. So you have to open the fibers, and typically it goes through a carding process, which is essential to individualize the fibers. And if necessary, you may have to go through combing to further straighten, align the fibers, and then do drawing. And then you produce the yarns, whether you go through roving or not, or you can go through other modern spinning systems to make the yarns. So there's a lot of mechanical process going on. As I already mentioned, these mechanical processes cause fiber problems and cause process problems, because these carbon fibers, as I said, generate dust material. And the opening devices tend to be very vigorous, okay, and they will damage the fiber, and they will generate lots of this dust material, which needs to be strictly controlled. I guess, this is dependent on where you operate. In this country, we certainly have a lot of difficulty, and we try to build a lab to do this, and it became almost impossible in the end. So we have to take an alternative approach, as I will describe in a minute. The other problem is during drafting, the fibers are too stiff and they're varying length. So they are not really moving very well because drafting obviously requires us to control the fibers so they move as they supposed to, so we can, deliver a strand with even distribution of fibers. So in the end, you will find that drafting carbon fibers becomes very hard. So a lot of people, as we will see again later on, using mixing methods by mixing carbon fibers with other fibers. Now that way we can use essentially the other fibers as carrier fibers to help the fiber through, help the carbon fiber through the drafting process. Dust material, I already mentioned, so I don't want to repeat. With the contamination of machines, quite often you'll find if we need to process carbon fibers, the whole machine and the process need to be completely enclosed within a chamber. Even in our lab, when we had a weaving of carbon fiber yarns, we had to build a separate sort of almost like a separate shed within the lab itself to prevent dust material spreading in other parts. In terms of the spinning techniques, I review these very briefly because it's relevant. So in the end, you have to turn the fibers into a yarn, suppose you manage to get all the fibers open up and draft it and into the required sort of thickness. So currently you can have ring spinning, which is very difficult to implement. And then rotor, of course, rotor is not very good dealing with dusty fibers. As I said, carbon fibers can generate lots of dust, which can cause problems. Obviously, air jet spinning is not going to work because of the way the fiber need to be, wrapping around the other fibers, and with stiffer carbon fibers, that can cause problems. So in the end, we realized friction spinning is probably the best in this case. There are other people trying other methods, but for what we have evaluated, that we have decided that friction spinning is more suitable because the idea of friction spinning is very straightforward. So you have two suction rollers, essentially, and they provide also friction to the yarn surface. And then you just need to spread the open fibers into this twisting zone, and then the fibers will be gathered up into a yarn. So you withdraw the yarn, in this particular case, perpendicular to the screen, so drawing it out parallel to the rollers, and that's all. So in terms of principle, as you can see, it's very straightforward. But again, trying to implement that becomes hard. And this is the commercial machine. So you can see this is the Draft 3, or sometimes called 3000 as well. Essentially, you have the fibers open up, and then you got the two friction drums, and you can also feed another drafted strand, which is important because there are people who does that with drafted strand, or you can also feed an additional core filament or core strand through. So you can one continuous strand core, one drafted core, and you have the sheath. So you can have compound sort of structures very easily using this machine. And this is somebody else's work. This is by Hassan, I think. Again, this is published in 2018. You can see here they are using a draft machine, but again, they are using a mixing of staple fiber, carbon fibers, and also nylon. As I said earlier, drafting of pure carbon fibers is difficult to control, so they use the nylon to assist that. And then they use another nylon sort of staple fiber coming from the top. And then they also fed another nylon filament through the center. So you can see a lot of nylon fibers involved in actually making the eventual yarn, just because pure carbon fibers are hard to handle. Now, of course, this does not resolve the problem of dust generation. Now, you can get away in some parts of the world, I think, depending on, but you still have to be very careful. But in certain parts of the world, like here, the health and safety control is extremely tight. So we tried to do something similar, but eventually we got blocked. So we had to try something else. And in the end, we've decided to use a wet process. Earlier, I talked about the wet laying in nonwovens. So we sort of try to combine wet laying with friction spinning. So by dispersing the carbon fibers in a liquid. And then we transfer the liquid. Instead of using air, we use liquid. Transfer that to the friction drums. This way, we can contain the carbon dust, so there won't be any dust generation throughout the whole process. And that's the video that what we built, just to show you the machine we have built for this. So that's the friction drums there, and you can see a lot of duct material for transferring the fibers in solution, and then you of course have a winder to take up the yarn. So that's the essence. So this is the spinning zone where the fibers are carbon fibers will be wrapped around a core. Again, we had to use a core fiber in order to get the yarn out. So it's not a purely recycled carbon fiber yarn. It's a sort of composite with a core fiber. Then we have the carbon fibers spun around that. And these are sort of some yarn samples we produced. One of the issues you can see is the fiber alignment is not great. So there are still lots of work to do in terms of trying to optimize the process. And this is something we've carried out in terms of looking at the composites made from these yarns with sort of different fiber length and different drum speed and also yarn linear density. What you tend to see is as the fiber becomes longer and also when the drum speed becomes higher, the composites tend to get stronger, which is understandable because longer fibers, especially given the poor alignment, the longer fibers will help to improve the yarn strength, because inside the composite, of course, there's interaction between twisting and the resin. I say that because in a normal yarn, the strength of the yarn comes from friction only, because between the fibers. But in the composite, you have the resin, which is like a glue to hold the fibers. So there's a lot of these different interactions going on. The other thing is that at the drum speed, with the increased drum speed, obviously it's like in any yarn production system, when the twist increases, the yarn becomes tighter. Okay, so that helps to make the yarn more compact, getting better strength out of it. But compared, if you look at straight comparison, you will find the composites made using spun yarns are still much lower, about a quarter to 1/3 of composites made from virgin carbon fibers. But however, the fiber volume fraction within the yarn composite, spun yarn composite, is much lower. So relatively speaking, actually the strength is not that bad. Compared with randomly aligned, in other words, non-woven composites, it's much better anyway. So we can improve it, but again, as I said, there are still plenty of work to do in this aspect. We are still working. Every time I click the slide, they seem to mute my mic. So things that we have to further resolve. One is the dispersion of the fiber. So the better the fiber is dispersed, the better. The more evenly dispersed the fiber is, the better the eventual yarn. And that way you can reduce the entanglement. As we know in any spun yarns, any fiber entanglement is going to cause problems in the yarn structure. And what ideally we want is the yarn, all the fibers to be aligned in the twist direction. And that way we can control the strength of the yarn much better. The other thing is actually is the life cycle assessment in terms of the actual costing. And because you can try a lot of technical developments, but in the end, if the process is not economically competitive to virgin fibers, because we go through a lot of reclaiming and then reforming, we haven't really done any calculation in terms of how much actually energy and labor input that's required to actually achieve the eventual composite. And we're hoping, because the process is cheap enough, it is still economical, but we don't know unless we do a proper assessment. Life cycle assessment is quite popular at the moment with a lot of recycling processes. Now we are also exploring other options. Some we have, some we are trying. This is using because, as I said earlier, during the process of using recycled carbon fibers, we realize there are a lot of dust material being generated. Now, one of the ideas, can we actually use those dust materials, the carbon dust? So we try to use that to produce compound yarns or compound filaments. In this case, we try to use that with polypropylene spinning, using using a resin with these dust material to be filled in as a 3D compound, 3D printed material. So originally you can, of course, print a 3D solid material, or you can using a resin filled one, or you can use RCF plus the resin and then fill it up. And we'll find actually with recycled carbon fiber filling, we can actually improve the strength of the 3D printed parts. Okay. So that's very promising. The other one is to use compound spinning by mixing sort of recycled carbon fiber sort of dust material with polypropylene and then spin it. And we also try to mix it with graphene. Of course, we are in Manchester. We are using graphene almost in everything nowadays anyway. And this is done with collaboration with the Graphene Engineering Innovation Center. It's on campus. They are, of course, mainly collaborating with industry, not really with academics, but still, for this one, we had an industrial participation, so we managed to do some work here. It's not very successful at the moment because we found actually by mixing these recycled carbon fiber materials in there, we actually had a fairly short, fairly lower strength, even with graphene, so it didn't work too well. Okay, but we hope, you know, there are certain things we can look into trying to improve it. The other thing is to using tape instead of making them into yarns by converting the recycled fibers into tapes, which of course has alignment. I won't want to describe too much in detail. Again, we have a product, we have a publication on this. Again, you can find this information very easily. Finally, just, you know, we're also considering using 3D nonwoven processes, trying to make 3D shaped products directly. And this is based on what we have already developed in our lab, a 3D forming process where you can actually form 3D nonwoven sort of composite directly. Okay, this is also published in Composites. Sorry, in the journal Polymer Composites. So all these have been tried already in terms of the process. We're just trying to use a different material to use the process. So that's the publication details. Okay, I think that's really all I want to report to you. Thank you very much for your attention.
Thank you very much, Professor. We have a few questions. One of the questions is Dr. Kashif Bangash. During spinning, the conditioning play a vital role in controlling dust. What do you suggest regarding conditioning during carbon fiber spinning, friction spinning?
Sorry, can you repeat that?
During spinning, the conditioning play a vital role in controlling dust. What do you suggest regarding conditioning during carbon friction spinning?
Conditioning. What does that actually mean, conditioning? Are you talking about applying spin finishes or? I'm not entirely sure what. Hey, the dust material usually is controlled by suction.
Okay, and
moisture.
He's asking about moisture. Moisture.
Like
moisture.
the environmental. Yes, environmental parameter.
Yes, because whatever you do, because carbon fibers is hydrophobic, so it won't absorb anything, and it will remain brittle. So you may, unless you get it really wet, so the dust doesn't get airborne, but that will have implications in terms of the processing because the fibers will stick to each other. So yeah, there are a lot of issues involved in this.
Experience regarding dust while having higher or lower moisture in environment during the process.
Yes, you can try to do that. I think, as I said, I mean, it's not something we've tried, but I think it's worth considering. But remember, dust material, the environmental, the moisture will have implications in terms of the machine as well. And if the dust gets into the moisture, where are they going to go? Are you saying the dust will not get airborne? They are going to stick to the machine or within the fiber? This is something I'm not quite sure. Because if they are airborne, you're going to still have the same old problem, whether you have moisture or not.
Okay, thank you, Professor. There is another question.
Okay, so we have another question that in which form of the recycled fiber was added to PP during the melt spinning? Please share your observation on its dispersion in PP.
Oh, you mix it in the polymer chip, in the chip form. So the PP comes as a bit like rice grains, and then you mix the fiber in there and melt them together.
Form or powder form?
Yes, in the powder form, you disperse that. And also, as I say, powders are different. There are powders which, in terms of what actual length, the size of the powder is important.
Thank you, Professor. But we actually tried converting the carbon fiber into powder, but the problem we are facing with is that in ball milling, we have this problem of conductivity. So how you achieve the conversion of recycled carbon fiber into powder?
Yes, the dust, the conductivity. Are you talking about problems caused to the machine?
Okay, so Professor.
Yeah, if it is the machine problem, then the machine design need to be improved because the machines we buy to process carbon fibers need to have very good insulation.
How about the dispersion of carbon powder in PP melt?
Yes, that is important, of course. You saw in our slide, the dosage is very low at the moment. It's only 1 or 2 percentages. So yes, it is an issue. So there are people trying to, what they do is they dose a small percentage, they spin the fiber, then they cut it, respin, dose again, gradually increase the eventual sort of carbon fiber content.
Okay, thank you.
Okay.
Thank you, Professor. Thank you so much.
It's my pleasure. Thank you very much for inviting me.
Thank you.
Okay. Shall I leave the meeting now?
Okay, meeting short.
Yeah, you can leave. Thank you.
All right. Thank you very much. Goodbye.
Thank you.
Closing.
This was the end of the technical sessions. We had a parallel session as a poster competition today. Here is the result. We had 3 positions. On the 3rd position, there is student Akib Salim. And at the 2nd position, the student was Adila Batul. And on the 1st position, it was Sabah Parvez. Thank you very much. Now, I would like to thank all the keynote speakers, presenters, participants for their valuable time and for sharing the innovative ideas. As we conclude the International Conference on Polymers and Composites, I am filled with the gratitude for the vibrant exchange of ideas and knowledge that has taken place over 2 days of Colloquium. Thanks to our outstanding speakers, presenters, and organizers, we have delved into the forefront of material science. Let's carry the inspiration gained here back to the respective endeavors, fostering innovation and collaboration. Thank you all for making ICPC 2023 productive and successful. Now, I would like to invite Dr. Zakaria Zubair to give closing remarks. Thank you so much.
Thank you very much. Assalamu alaikum and good afternoon to all the participants. Thank you to each and every one of you for being here with us for 2 days at the third annual event of ICPC. There were 7 technical sessions and 28 speakers, including keynote talks from the University of Polito, Italia, University of Manchester, UK, Khalifa University, UAE, University Technology, Malaysia, Northumbria University, UK, GK, Pakistan, UET, Peshawar, Bursa University, Turkey, Marmara University, Turkey, University of Agriculture, Pakistan, University of Wa, Pakistan, Taveta, Pakistan, Austin Technical University, Ankara, Turkey, University of Kotli, Pakistan, Quaid-e-Azam University, Islamabad, Queen University, Belfast, UK, University of Swat, Pakistan, Jinnah University for Women, Pakistan, Donghuk University, Seoul, South Korea, the University of Faisalabad, Pakistan, Panther Tire, Pakistan. I would like to thank all the national and international speakers from these universities and Rector, National Textile University, Professor Dr. Tanveer Hussain, Dean SCT, Professor Dr. Yasir Nawab, and HOD Department of Material, Dr. Khubaib Shakir. I'm also indebted to the ICPC Organizing Committee, including faculty members, staff, and students from the Department of Materials and National Center for Composite Materials for their contributions to making this event a success. Hope to see you all for a physical gathering at the 4th event of ICPC next year. Once again, thank you all for your participation.
Thank you so much, Dr. Zakaria Zubair. Now we have reached a momentous juncture in our event, the certificate distribution ceremony. This is the time to honor and recognize the dedication, hard work, and achievements of those who have contributed to success of this gathering. Before we proceed, I would like to extend my sincere appreciation to all organizers for their valuable contributions. Your commitment to excellence has made this event truly exceptional. Now we'll begin the distribution ceremony. So we have a short break of 5 minutes, then we will proceed to the distribution ceremony. Now we have reached the momentous juncture in our event, the certificate distribution ceremony. This is the time to honor and recognize the dedication, hard work, and achievements of those who have contributed to success of this gathering. Before we proceed, I would like to extend my sincere appreciation to all organizers for their valuable contributions. Your commitment to excellence has made this event truly exceptional. Now, I would like to invite Dr. Hubaib Shakir to present the certificate to Dr. Yasir Nawab, the conference chair.
Okay.
Next, we have Dr. Zakaria Zubair, the chief organizer. Dr. Asif Hafiz as organizer. Dr. Zubair Khalik as organizer. Dr. Kashif English as organizer. Dr. Wasif Razak as organizer. Dr. Faiza Anjum as organizer. Dr. Amjad Javed as organizer. Dr. Muhammad Umair as organizer. Dr. Habib Awais as organizer. Dr. Zishan Ali as organizer. Mr. Muzammil Mahmood as organizer. Ms. Ikra Abdul Rashid as organizer. Mr. Ahsan Ahmed as organizer. Mr. Zubair Jilani as organizer. Mr. Suhaib Arif as organizer. Mr. Tahir Khan as organizer. Mr. Zishan Altaf as organizer. Mr. Farooq Anwar as organizer. Mr. Muhammad Akmal as organizer. Mr. Hamza Tariq as organizer. Mr. Numan Farman as organizer. Mr. Hamza Sadiq as organizer. Mr. Hassan Ali as organizer. Now I would like to invite Dr. Yasin Nawab and Dr. Zakiya Zubair to present other two certificates. आप भी डॉक्टर को बैठ को नहीं करना सर्टिफिकेट देना